In this video, I'm going to fill in the process for conducting a one sample hypothesis test. And the first step is to state your hypotheses. Now, we practiced this in a previous video, which was about stating hypotheses. And there's going to be two tests that you would likely be doing in this course. And that is one for making an inference about the population mean, which is, again, that notation there. Or you might be making an inference about the population proportion, which is the second column on the right. If you are drawing an inference about the mean, if that is your goal, then you've got three possible sets for hypotheses. And you saw all three of these in that practice handout that was used in the video. And so your null might be less than or equal to some value or some constant c, and the alternative would be greater than, or it may be greater than or equal to in your null with less than in the alternative hypothesis, or it could be equal and not equal. The same symbol pairings show up on the proportion side too. And so the only thing that changed is the parameter itself. Either you're drawing an inference about a mean, an average, or about a proportion, a percentage, a probability. So that's really what changes with your hypotheses. In step two, you would compute an appropriate test statistic. So this is new. This wasn't covered in a past video. And this first formula is one that you've seen before. This is if your sigma is known. So remember, the central limit theorem told us that x bar has a normal distribution with a mean mu and a standard deviation sigma over root n, or variance sigma squared over n, but when you square root that, you get sigma over root n. And so you've seen that, you've used that formula before to convert a mean, an average, into a z-score. And then the next formula below that is one you haven't seen, but you likely could have deduced. And so when we were working on confidence intervals, remember that there's a case where if sigma isn't known, a couple of changes happened. And one of those changes was that you change sigma to s. And when you're using s, you also change z to t. And so it's a small but comparable change that happens with your test statistic formula. And again, the decision process is the same as what we used for confidence intervals, which is if sigma is known, use it, and it's a z-test. If it isn't known, estimate it with s and use a t-test. Now this z and t, they are calculated. So unlike in the confidence interval approach, where z and t, which I usually put stars on them, are critical values and are table lookups, these z and t's are test values or test statistics and are calculations. And so I put the asterisks on them to differentiate them with a confidence interval as opposed to in a hypothesis test. And then finally, one formula that you haven't seen is when you are drawing an inference about P, your hypothesis test statistic is going to be given by this third formula here. Notice that the square root has P and Q, not P hat and Q hat. So the square root term in a confidence interval did use P hat and Q hat, but for a hypothesis test, there's no hats. Those are your population parameter values. Step three is another one that you saw in a previous video, and this is finding critical value or p-value. You haven't seen the p-value yet, but I'll talk about that in a moment. But you have practiced finding critical values. And again, if your sign in H1, the alternative hypothesis, is a less than sign, your critical value is likely going to be negative in your rejection region on the left, like the picture shows. If you have a greater than sign, your rejection region is going to be on the right. And if you have a not equal to sign, then you are splitting your rejection region onto both sides equally. So that's a step that you've had practice with. Step four is to make a decision. And there's only one of two decisions that you would make. Either you reject the null hypothesis or you fail to reject the null hypothesis. Some of you may have prior experience with statistics, and you may have had a teacher that uses the phrase accept, like accept the null, accept the alternative. But in practice, you really never accept. Either you have evidence to reject or you fail to have evidence to reject the null. And so those are formally the two correct decisions that you can make. And the way that you do that is if your test statistic is inside the rejection region, then you're going to obey the name of that region and you will reject the null hypothesis. So in other words, if we were doing a left-tailed test, like in this top figure, and let's say our test value or test statistic was here, since that's inside the rejection region, we would end up rejecting. If it was a right-tailed test and our test statistic was here in that second diagram, we would fail to reject the null hypothesis. And likewise, if we had a test statistic there, what do you think we would do in that third case where you have a two-tailed test? Hopefully you said to yourself or called out loud that you would reject, and that would be the correct decision. If you get a p-value, and again, I know I haven't told you how to get that p-value just yet, but if you get it, and it is less than or equal to the significance level alpha, that's what alpha is. So this is the only relationship you're looking for. If the p-value is less than or equal to alpha, you reject the null. Otherwise, you fail to reject the null. That FTR is my shorthand for fail to reject the null. And then finally, you would interpret your results. And when we get to applying these methods, you'll see how to interpret. I have a similar trend to what I did with confidence intervals. But at this point, I want to give some more instruction with respect to how to find p-values, because that is the more common approach to use in practice, but it typically is a harder one for students to get used to. So let me fill in the gap there. And the way you get a p-value depends on which test you're doing, which one-tailed or two-tailed test you're doing. It doesn't differ whether it's a Z or a T test, it just differs on if it's a left-tailed, a right-tailed, or a two-tailed test. All right, so let me fill in that gap there. And let's start off simple. And I'm gonna start from the bottom and work my way upwards. If we are doing a right-tailed test and the p-value, knowing that that corresponds to the probability of being more extreme than your test statistic, then the only thing that you may not know is what is extreme. And the good news is that it's pretty easy to figure out. Extreme is the direction according to the sign in H1. So let's pretend that our test statistic for a right-tailed test was here. And I'm just going to pretend that that number is 2.75. And if this was a z-test, then the p-value would be the probability that our test statistic is more extreme, and this is a right-tailed test according to the sign H1, which I've got on the left side there, more extreme than what we observed, the test statistic of 2.75. And you have lots of practice with this in a few videos ago, where you would then use your standard normal table in order to find what this probability is. And so that would be your p-value. If you, let's pretend that we had the same test statistic here in that middle figure. And so this is z equals 2.75. In this case, the p-value would be the probability, and if it's still a t-test, or sorry, a z-test, it would be the probability that z is less than 2.75. Again, because for this picture, it is a left-tailed test. And so whatever this lookup is from your table, that would be your p-value. What if We have this case here, the very first one, where z, our test statistic, is 2.75. And so in this case, because it's a two-tailed test, even though we observed 2.75, since both regions, both tails are in play, the mirror image could have been possible. It could have been z is negative 2.75. And so when we are computing the p-value for a two-tailed case, this is going to be the probability that z is less than the negative part, or, and or is plus, or greater than the positive part. But by symmetry, we know that those two areas are going to be the same. And so this is identical to 2 times the probability of either one of these. I'll just go with the left-tailed one. Z is less than negative 2.75. And so when you're doing a two-tailed approach, you're probably going to have to multiply one of those tails by 2. You just need to make sure that you pick an appropriate one. And either would be fine. I could have done 2 times the probability z is greater than 2.75. The reason I went with the less than one is because it's less than a negative z-score. And I know from experience that the standard normal table gives that exactly. And so that's why I chose that one, but you could have worked from the right tail too. So that's how you get the p-value. The approach differs depending on which tail it is, but once you get it, regardless of which method you had to use, you are going to look for this comparison here. If your p-value is sufficiently small, if it's less than or equal to alpha, you reject the null hypothesis, and that would be your decision. And that's it for this video. In the next one, we're actually going to get to applying the whole process to a variety of examples.